would all cheerleaders please head to the cafeteria?
We're going to start with
now?
part
All
2, the proof
cheerleaders,
part.
You need to go to the cafeteria, please.
Unfortunately, I can't see.
So again, you rewrite the question, you draw your line. Pages. This is page 609. And we're going to use the main strategy. So the main strategy is you change everything to sine and cosine. And once you change it to sine and cosine, can you simplify and get a single fraction on both sides? So for here, cotangent is cos theta over sine theta. And notice how I make it like a bigger main line, and then cosecant is 1 over sine. So now I have fractions inside of fractions. Where the strategy is if you have a single fraction on the top, which we do, and a single fraction on the bottom, which we do, you can now multiply by the reciprocal. So I would have cos theta over sine theta multiplied by sine theta over 1. And these are identical. We're multiplying, so if you have factors that are identical when you're multiplying, you can simplify, and this just becomes cos theta. So we do a quick check. Hey, that's what the other side is. Yay, we're done. Left side equals the right side.
Excuse me, John, students, can I get the grade 9 and grade 10 student council reps, please, down to the office? That's grade 9, grade 10 student council representatives to the office. Thank you.
Now, part 1 of this question had asked about where things were undefined. So, in a proof, just like anywhere else, you're never allowed to divide by 0. So I took my highlighter out, and I'm just going to highlight everywhere that I'm dividing by something. I don't have to highlight the 1, because 1 is never going to equal 0. It just so happens in this whole one, after you've changed it to sine and cos, the only thing you're dividing by is sine. Does it make sense then for a non-permissible value that sine of theta can't equal 0? Because then you would divide by 0. Which means that theta can't equal, from chapter 6, do you remember all the zeros of sine? Zero, pi, 2 pi, 3 pi. So we can write k pi saying all the multiples of pi would not be allowed.
Can I use just any letter?
Yeah, I don't know why k is used the most in this case, but yeah, you could use n pi and say n belongs to integers.
Although n pi would be kind of weird to look at because pi already kind of looks like an n.
Yeah, and it would be weird to use the Greek letter pi for your variable, because then you'd have pi, and that would be weird. I don't think that would be a good idea at all.
Would we be allowed to use it as a variable?
Probably
in a
not.
question that already has pi?
Because it already is meeting a number. So let's look at the second one. Again, we're going to prove it first, draw the line, and again, I'm going to use the main strategy. So the only thing that's not cos is this secant, so I'm going to change that secant to 1 over cos theta. I'm going to rewrite out, we wrote this before. When you have fractions inside a fraction, like we have a fraction that's inside a bigger fraction, our main strategy was get a single fraction on the top in your numerator and on the bottom in your denominator. So it's just a little review, because things go bad if you try to do anything before that. Like if you try to multiply by the reciprocal now, it just does not work. So first of all, we have to get a fraction in the top and a fraction in the bottom. Technically the top is a fraction. It has a common denominator of 1. The top is 1 plus cos theta over 1. It is a fraction. The bottom isn't a fraction because this is 1 over 1, and in order to add fractions, I would need a common denominator. So I'd have to multiply top and bottom by cos theta, which would give me a common denominator of cos theta, and then I would have cos theta plus 1. So for fractions inside of fractions, I want this step. I want a single fraction on the top and a single fraction on the bottom, because now I can multiply by the reciprocal. So I keep the top fraction the same, and I multiply by the flip, or the reciprocal, of the bottom fraction.
Question, yeah, question about, the one you did with the blue little thing there.
Mm-hmm.
I'm confused, shouldn't it be like 2 cos, theta?
What I'm wanting to do here is I want to add 2 fractions.
Yeah.
And I need a common denominator,
The common denominator is the cos, right?
is the cos.
Yeah, but it's.
You're wondering if it should be a 2 on the bottom here?
Yeah,
Okay, what do you do when you add this? Is the answer 7 over
Oh,
2
yeah.
3s, or is it just 1?
yeah, I remember one.
Yeah.
Yeah, plus with fractions, like,
Right? So again, if you're ever, and this is what trigonometry with fractions is going to do. It's going to strengthen your fraction rules. Because you're fine when they're nice numbers, but all of a sudden, when it's sine and cos, now you start to second guess your rules. So if you're ever unsure of something, go back to nice numbers and decide, oh, what did I do when the numbers were nice? Does my denominator change? No, it stays the same. Okay. Next, for simplifying. You can only simplify if factors are identical and you are multiplying. So notice we are multiplying right here. And when things are added and subtracted, you might want to add brackets because they are grouped together and considered a single factor. So can you see though, in those brackets though, 1 plus cos theta and cos theta plus 1 are identical. So I would be allowed to simplify them away. And you always want to simplify, like you could have distributed, but that would actually make your life more difficult because then you wouldn't have simplified. So you want to check that you can simplify, and in this case, once those go away, we just get cos theta. What was the first side? Yes. And now the non-permissible values for theta. So I can take out my highlighter again. And after I've changed the sign and cos, I check, where am I dividing? I'm dividing here, I'm dividing here, I'm dividing here.
just a question.
Yes.
If we had, in the blue brackets, one is 2 plus cos and one is 1 plus cos,
They
I could not
No.
put the cos, okay, good,
could not cancel them out.
understood.
You're gonna be tempted, I'm telling you, this is a unit of temptation. You're gonna be tempted to cancel out things when you're not allowed to. Because wouldn't it be nice? But make sure you're following the rules. So I highlighted everywhere that I'm dividing. And this time, not only do I get cos theta, that can't equal 0. So I don't know if you remember, that is, cos theta is at 0 at pi over 2, and then every jump of pi, you could write it that way, or you might have remembered we also could do the 2k plus 1, pi over 2, where it's odd numbers of pi. But we also have right here cos theta plus 1 on the bottom. So it's going to be bad if cos theta is negative 1. That would cause us to divide by 0 there. So we have additional places. Anywhere where it's pi plus 2k pi. Again, we've got a little bit of the general solution here. Yes.
Wouldn't sleeping theta also not be able to be 0?
and secant theta couldn't be -1. If you change to cos, sine and cos, and check it after that, it'll do the same thing, you don't have to check the secant right at the beginning. Because technically, secant theta, look what happened, secant theta can't equal -1, so that means that cos theta can't equal 1/-1, which we have already listed. So changing it to sine and cosine and just checking those will be enough for checking your non-permissible values. Because one way that you would check any secant or cosecant one is you'd have to change it to sine or cos anyways to find out. Okay? This strategy in green, though, is going to happen lots. And if you multiply by the reciprocal too soon, your proof will probably fall apart. Okay, so the simplest strategy is if you can get a single fraction by adding or subtracting, getting common denominators on the top and the bottom, then multiply by the reciprocal, life is going to be a lot easier. Okay. I am going to get you to do circle questions 4, 8, but just do the proof, I, 9, just do the proof, I, and capital II, or 11.